So computational graphs really make this whole calculation much faster. But there is one problem with TensorFlow. What is the problem? We need ready-made functions while we are building models. For example, if you are building a simple regression line or simple logistic regression line, are we directly solving the problem by ourselves, or we are using a ready-made package? Are we sending the data and then are we calculating the error, which is sum of squares of error? Are we writing the code for calculating the derivative of it, finding the minimum value, and then are we writing the code for calculating the beta naught, beta 1 values, or we are directly using a package that will take care of everything internally, give us the results? But now with TensorFlow, we are back to square one. We are back. That means again you have to start with, you give the data, you define the error function, which is also known as cost function. You define the optimizer. Optimizer means which kind of derivative that you are going to use for solving this problem and to get these results. That means we are again back to the basics. That means to build a model in TensorFlow, you have to define the model equation first, and then you have to define the cost function. In our case, it is sum of squares of errors is the cost function, and you define the optimizer. That means you have to say, I have to use gradient descent or some kind of derivative that will calculate me the values of beta naught, beta 1 and give me the values. Now, if still with this error hasn't reduced, then again, you are going to repeat the same process of reducing the sum of squares of errors and calculating the values of beta naught and beta 1, isn't it? Okay. So we will see how to build models in TensorFlow first of all. All of you open the code file, then I'll try to explain you how to build the models in TensorFlow. Okay, let us open the code file. First, we need to install TensorFlow, pip install TensorFlow. If it is already installed, you can check the version, import TensorFlow as tf dot underscore underscore version underscore underscore will give you the version of the TensorFlow that we are currently using here. It must be above 2.0, okay, which are here we are using 2.3, okay, which is the latest available version given by Colab to us. Import NumPy. Okay. Now this is the data that I'm creating. This is random values of x. I have taken 3 times x is what I have created, which means y equal to 3x, which means I have to get w value. So basically what I'm trying to do in this simple example is I'm creating random values of x, okay, that are between 5000 to 5100. This is the value of x. Y equal to 3x is what I'm creating. Y equal to 3 into x plus some random value also added, some 500 or something is added here. Okay. So basically I have to get y equal to 3x means I have to get if y equal to beta naught plus beta 1 x, then I must get beta 1 as 3 at the end of the output. A simple data set has been created here. Okay. In fact, if you look at it strictly, I think it is 3x plus 10 is what we are creating, y equal to 3x plus 10 roughly. So we already know the answer. Beta naught will be our 10, beta naught will be 10, beta 1 will be your 3. So this is the data that we have created. Now we are going to solve this problem. If you are writing this code, then what are the steps? First, you have to create the model equation y equal to x w plus b. W is the weight matrix. This is a generic form of writing it. Instead of writing y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 etc etc, instead of that, the usual way to express this is x1 x2 and so on is a matrix. So that is explained like this, expressed like this: x beta naught, beta 1, beta 2 and so on, that is a weight matrix that is expressed like this. In fact, beta naught is taken separately, that is left it as it is, because in our neural networks also we are making this x1, x2, x3, and then 1 into beta naught or w naught. So that is expressed separately. That is known as b here, bias term b. So this is how it is expressed, which is nothing but our usual linear regression line. This is my model equation. So we are actually writing everything on our own here. Model equation, define the loss function, sum of squares of errors need to be minimized. Now, how do you solve this problem? We solve it like a neural network problem. You initialize the W values, you initialize the W values, you initialize the B value, which means initialization of the weights. Then you define something called learning rate or the steps. We are going to come to learning rate later on. Then try to solve this whole problem using this gradient descent method. That means you supply these values of weights. Do you remember that? You supply the values of weights, make the calculations forward, calculate the error, and then find the back propagation. Try to move the weights in such direction that this error will reduce. Like that, this whole process will happen in these 4 steps. Then the model will be built. Right now, this is the way we have to do it in TensorFlow, which is very much code intensive. Later on, I'm going to tell you a shortcut. Okay. As of now, I'm highlighting the problem here. There will be a solution for it. So even if you don't understand this code, it is perfectly fine. We will not be writing like this ever. We will be using a ready-made package later on. As of now, if you strictly talk about TensorFlow, you have to write the code like this. If you want to build a logistic regression line, then instead of wx plus b here, we will be using sigmoid. Basically here model equation will be sigmoid, then the cost function, then the optimizer as usual. So instead of that, we will be putting a sigmoid function there, sigmoid of wx plus b. That means e power beta naught divided by 1 plus e power beta naught. Let us go back to the code. So I'm building a linear regression line here. So with all those steps, if we execute, first we have to define x train and then y train. So this is our data, and at the end of it, several like internally whatever is happening, we can see it here. Finally, w has been predicted as 3, b has been predicted as 1. Okay, so basically 3x, as we expected, it has to be 3, value 3, which has been predicted. The final weights w will be our 3, value 3. Where is it? 3.0982, and value of b is 1 here. Similarly, if you are building a logistic regression line, here is the data that we have created for the logistic regression line. This is the data. This is a class 0, class 1 scenario. We are going to build a logistic regression line here. We are taking 300 epochs roughly, and W will be 14, B is -7. This is how you write the code in TensorFlow. Strictly, if you ask me how to write the code in TensorFlow original version, this is how we write it. But this looks like a disadvantage. We will discuss about the disadvantages and the solution after this hands-on exercise. Go ahead, execute this. Let me know if you have any questions. Now, the advantages of TensorFlow that we have seen is it is very fast. Okay. It can make complex calculations very easy. It can do parallel processing. You can use GPU. All these are fine. That is fine. But the problem is a lot of low level coding is required. And it will be very difficult for somebody who is not from hardcore coding background to work with TensorFlow. A lot of things need to be done again and again, and there is a high chance that we might be writing wrong piece of code in between. For a single linear regression, logistic regression, we have to write this much of code. If it is neural network with multiple hidden layers, there will be hell lot of code. There is a high chance that we may go wrong. Is there any wrapper on top of TensorFlow that can take care of all these things automatically? That means the usual way, how we want to do it, we want to give the data X and Y, that's it. Hardly we want to mention how many number of hidden nodes or hidden layers, that's it. Everything else should be automatically generated. The TensorFlow code should be generated by that particular package, and automatically the model should be built. I should get the results automatically. Everything should happen automatically. I just want to give the data and then I want to get the results. Now, what is that package that can do all these calculations automatically? The package name is Keras. Keras, in simple words, TensorFlow programming made easy. Keras is a wrapper on top of TensorFlow. In simple words, if you understand, in Python, everything, all the calculations are done in NumPy. Okay, on top of NumPy, for doing regression, logistic regression, your decision trees, everything, there is a package that works internally with NumPy, but you don't write the code in NumPy, but you give to that package. Can somebody tell me what is the package that is built on NumPy that we will be interacting to build machine learning models that will give us the results? Do you know that package in machine learning models? If I'm talking about logistic regression, linear regression, or your decision tree models or boosting, which package is there written on NumPy which we are interacting, which will directly give us the results? That package is sklearn, isn't it? You give the code, you directly give the data in sklearn, and then you will get the result. Similarly, internally you are doing everything in TensorFlow. What is the package that you can interact easily and get the results easily? That is Keras. In the starting, Keras used to be a different package or a different tool. You have to install TensorFlow separately. After that, you have to install Keras separately for the first 3 years, 2016, 17, 18, even 2019. Okay. Later on, Keras become so famous that so everybody was using Keras only. Nobody is writing, or very few people are writing TensorFlow hardcore code. TensorFlow has now included Keras along with TensorFlow code itself. That means if you install TensorFlow, it will automatically install Keras also right now. Now TensorFlow, Keras is a part of TensorFlow. Even in the original documentation, they are giving the whole documentation in the Keras only. So in fact, future generation, they will never get to know that Keras used to be a different package, which is other than TensorFlow, which was a different API written on top of TensorFlow. Nobody will get to know. Keras is right now very much part of TensorFlow. In fact, I am also going to remove these slides later on. When I install TensorFlow next time onwards, maybe after a few years, I will directly include Keras. I will actually get rid of this complex coding. This I will not even call that as TensorFlow. Directly we will be doing it on Keras. Keras is a wrapper on top of TensorFlow. What does Keras do? You give a command, it will take the pain of converting that command into TensorFlow code, then generate the output, show you the output. Very easy. One line of code, you have this whole code created, one function. If you call that function, TensorFlow code will be created background. Okay. Very easy to learn, very easy to implement deep learning models. Everybody uses Keras these days. Okay. It is one of the best wrapper. Almost, I think there is no other wrapper. Very few people know other wrappers, but this is one of the best wrapper on top of TensorFlow. Right now, it is very much part of TensorFlow. Now we will not say on top of TensorFlow. Keras is also part of TensorFlow. Very good for non-coders, somebody who has very less background in coding or syntax and all that. Keras is the one. Damn good documentation. In fact, even Google right now is documenting everything in Keras only. Earlier, there used to be two versions. One version in Keras, the other version in TensorFlow, like the extended version and this one. Now, automatically, they are eliminating all these TensorFlow ones. Everything will be written in Keras only. We're going to see one example and how to write the code in Keras. Okay. There is a particular coding paradigm this Keras follows. Once we understand it, then building or writing the code for deep neural networks will be very easy. So first you have to prepare your data. That means import the data, prepare the train and test data, etc., which is an easy step. You configure the model. While configuring the model, there are particular steps that we need to follow. This is a place, while configuring, that is a place where we'll be spending a lot of time. Compile the model, because this model calculation takes a lot of time. compile the model, make sure everything is fine, there are no coding errors and all that. Then finally you train your model. Then model training. So when you say train the model, automatically behind the scenes TensorFlow code will be created. It will be executed. Okay. So while you are configuring the model, you have to add input layer, you have to add hidden layers, you have to add output layer. In a sequence manner, you have to add input layer here, model.add, model.add output layer, hidden layer, model.add output layer. Like this, we have to add one by one. Okay. So let us see a simple example. Then we will try to understand what exactly the sequence of layers mean. Basically, the first hidden layer you need to add. So basically, whatever is our overall ANN structure, that need to be mentioned in Keras. So my input layer has this much shape. That means these many rows, these many columns are there. And then hidden layer has this structure. It has one layer, these many nodes are there. It has, otherwise if you have one more hidden layer, add one more hidden layer. My output layer has these many nodes and it is connected to hidden layer. These inputs we are going to give while building the model on Keras. Okay. Let us go back to that digit recognition problem. If you remember, the previous digit recognition problem that we worked with was 16 by 16, which was 256 nodes were there. And we worked with around 7,000 odd records. Do you remember that 16 by 16, 256 nodes were there, 7,000 odd records? That took 200 seconds. Now we are going to work with even larger data sets here, okay, which has not 7,000 records, roughly 60,000 records are there. Even it is not 16 by 16, it's even larger than 16 by 16. It is around 24 by 24, I think. Around 784 nodes are there. Here instead of 256, you have 784 nodes, 3 times the input nodes, and then around 8 or 9 times the data, and the time taken will be not 200 seconds. With this much large data, with this much of nodes, the time taken will be hardly 10 seconds. I think somebody made that math, right? Like if you're doing these parallel computations, how fast that will work? Hardly 10 seconds. That's it. Okay. So from TensorFlow import Keras, from Keras import layers. Earlier it was import Keras. Keras was a different tool. Now it is in TensorFlow. So from TensorFlow you import Keras. Okay. This is the data preparation. You get this data. This data is already in your Keras data sets. This is one of the default sample data one can try. Okay. So training data has 60,000 rows, which means 60,000 images. I think 24 by 24, which is like 784 would be your overall number of input nodes. And then your output has 10 nodes. So let us open the code file, and then we will go back to the code file and try to solve this. Okay. I think 28 by 28, I think. Yeah. Import this, and this is the data part. Right now, data importing is being done. So 60,000 records are there. 28 by 28, which will be 784 pixels. Okay. Now here is the major piece of code. All of you, once you understand this, then we are through. Okay. This is the most important piece of code. We will be referring to this code again and again, even in future, this style. Okay. Look at this carefully. Model equal to keras.sequential. That is a standard syntax that you have to write it. That means we are sequentially defining the layers. So be ready to take one by one. First, define the first hidden layer. While you're defining the first hidden layer, always mention the shape of the input. Okay. So our input shape is 784 columns, 784 column, and the number of rows can be anything. It can be 50,000, 60,000, 70,000. I can give any number of images, but each image has 784 pixels. Now, model.add, we are adding the first hidden layer. These hidden layers, every input layer is connected to every hidden node. Every node in the input layer is connected to every hidden node. Every node is connected to every other node. That's why they are known as dense layers. So layers.dense 20 comma activation equal to sigmoid input shape. I have explained you what is input shape. Input shape is nothing but your number of input nodes comma number of images you can give, otherwise you can ignore that. Okay, always the general standard is just give the number of input nodes. If we were solving our previous problem, what will be our input shape? Can you write that in the chat window? If we were solving our previous data set, which has 7,000 rows and then 256 nodes, what will be our input shape? How do I measure? How do I put it here? How do I mention it here? I'll be mentioning input shape equal to, at the place of 784, I'll be mentioning 256. That's it. Input shape is number of nodes in the input layer, x1, x2 and so on, x256, then you mention 256, x1, x2 and so on, x784, then you mention 784 here. Okay, point one. Now you are going to answer me in this first hidden layer. In this first hidden layer, how many hidden nodes are mentioned? How many hidden nodes am I mentioning? Can you see that and tell me how many hidden nodes? So input layer has x1, x2, x3 and so on, x784. Now this is our first hidden layer. Can somebody tell me how many nodes are there in the first hidden layer? Are we mentioning it here? Can you see this? Tell me how many. Check this out. How many hidden nodes are there? So in there, H1, H2, this is layer 1, model.add. So we are adding one layer with how many nodes? 20 hidden nodes. 20 hidden nodes, H1, H2, H3 and so on. H20, 20 hidden nodes are mentioned here. This is the number of hidden nodes. This is the first layer. So basically this is input layer, that need not be mentioned. You directly start with the first hidden layer, but in the first hidden layer you mention what is the input shape. Input shape is 784. From there we derive the number of input nodes, and then this is our first layer with 20 nodes. What about the second layer? Can somebody explain me the second layer with how many hidden nodes are we adding? Again, we are adding a second layer, second hidden layer with how many nodes? Again with 20 this is, let me call that as H21, H22, H23 and so on, H2 comma 20. What about this one? This is the final output layer, models.layers.dense. Here, this is the final layer, the layer that you mentioned the last time. This is connected to the output. Here, the sigmoid activation was used, which we know already, something like logistic. This is sigmoid, but in the final output, we have used soft max. What is soft max? In your final output, y1, y2 and so on, y10 will be there. Or let's say y0, y1 and so on, y9. 10 outputs will be there for every problem. For every image that you give, you will get 10 probabilities. For every image, you are getting 10 probabilities. But one image, you can give only one output, right? How can you give me 10 probabilities? Then what will be the output? Tell me. If you have to give me one output value out of these 10 probabilities, which one are you going to consider? Let's say you have given this image and the probability of becoming 1 is 0.2, probability of becoming 2 is 0.25, probability of becoming 3 is 0.01, like that probability of becoming 6 is 0.99, probability of becoming 9 is 0.28. Then which one will you give as one final output? The one that is the maximum probability. Class 6 has a maximum probability. I'll give that as the final output. That is what activation softmax means. You calculate all these probabilities, take the final output as the maximum probability. Has everyone understood this activation softmax here? It's a simple concept. You have 10 values that are given as output for every data point. Take the maximum probability, give me as a result. Have you understood this? Activation equal to softmax, all of you. Yeah, that is it. In fact, it's a simple hint for you that the output layer, usually we will have multiple classes. Activation equal to softmax is, that means it is the final output layer. You can check the model summary. Earlier we used to calculate the number of weights manually, right? So right now, if you have 784 nodes here, x1, x2 and so on, x784, and then if you have h1, h2 and so on, 20 here, in the first layer, how many weights will be there? Can you make a calculation? How many weights will be there? 784 into 20, yes or no? This will be x1, x2, x3 and so on will be connected to this one. If you add that bias term also, which is beta naught, beta 1, x1 and so on, then it will be 785 into 20. Do you agree with that point? 785 into 20, how much that will be? 15700. If it is 785 into 20, how much that would be? Calculate that. From here to here, from input to this one. Is this correct? Yeah, around this number only. What about the second one? You have 20 here. Again, you have 20 in the second layer. How many nodes will be there? This will be 21, like here 20 into 2400 plus we will say actually 21 because there is one bias, the one that is hanging in the air, 21 into 20. That will be like your 420 nodes and all that. When you say model.summary, you will also get this summary automatically generated for you in the first layer. From here to here, these many weights are there. From here to here, these many weights are there. From here to here, these many weights are there. That will also be given to you. You can also verify that. Okay. So here we have mentioned 20 hidden nodes in the first hidden layer, 20 hidden nodes in the second hidden layer, 10 nodes in the output because there are 10 values, etc. And when you check the model summary, you will get this 785 into 20, 15700, 21 into 20, 420, 21 into 10 in the last layer, 210. Are these calculations clear? What about 21 into 10? Last layer has y0, y1 and so on, y9, which are 10 nodes here. So what it will be 21 into 10, which will be your 210. Overall number of weights or the number of parameters are 16,330. Model.compile, mention the loss function, mean squared error, reduce the sum of squares of error or average sum of squares of error. Model.fit, x train, y train, epochs equal to 500. Do you remember the time taken for your previous model, which was a very simple model, 16 by 16 around 256? In fact, the number of weights during that time, anybody remember the number of weights? Here, the number of weights that we are calculating are 16,000 weights. Previously, instead of 16,000 weights, previously we were calculating 5,000 weights with around 7,000 records. That took on a usual Python program, it took around 200 seconds. Now with 60,000 records, 16,000 weights, it will take how much time? Let us check. All of you go ahead here. If you execute this, you will see how much time it will take to give us the same accuracy, which is around 90%. The accuracy already reached 90%. It didn't even take 10 seconds. Not even 10 seconds. 2-3 seconds itself, we have got the accuracy to be 95 or 90%. 10 epochs done. I think for each epoch it took hardly 2-3 seconds, maybe overall 20 seconds of that. Even if you check it on the test data, train data accuracy 95%, test data accuracy 94%. That is what Keras is all about. The major critical step in Keras is mentioning the model, configuring the model. While configuring the model, you are mentioning the hidden layer details one by one carefully. Hidden layer 1, hidden layer 2, hidden layer 3, and then finally your final hidden layer 4, etc. Finally your output layer. Okay. That is how Keras works. Go ahead, execute this. Once you're done with this, please let me know. Now that concludes our discussion on Keras and TensorFlow. Though I have introduced TensorFlow and a simple code of TensorFlow, in reality, we will not be writing the code on TensorFlow. We will be writing the code in Keras, which indeed internally converted to TensorFlow code, and we will get the output. The biggest advantage is its user friendliness, its modularity, easy to read the code, its extensibility. You can easily expand this code, and it's very easy compared to TensorFlow. Keras makes your interaction with TensorFlow very easy. Very less lines of code, very much tidy code. It is already having so many pre-existing functions. All that we need to do is call the right function and give the right parameters. Automatically everything will be taken care of automatically. Look at this here. We did not mention the data, we did not mention the cost function, we did not code it for back propagation and all that. Automatically, when we just configured the model, when we compiled the model and gave it to the algorithm, automatically everything has been done by Keras automatically. In fact, in future we will be using Keras for all our deep learning problems that we are going to try. Okay, any questions on this Keras? In fact, what I'm trying to tell you is, do not treat Keras different from TensorFlow. We should not say that I know TensorFlow, I don't know Keras, or I have worked on Keras, I don't know TensorFlow. Right now, both of them are considered as single tool TensorFlow only. By default, if somebody says I'm working on TensorFlow, maybe they are indirectly, they mean to say they're working on Keras only. Even in the original documentation of Google, when you, let us suppose, when you want to search for the code of building the model using Keras, you might get this type of code only. Using TensorFlow, if you search for it, nowadays you will get this type of Keras based code only. You may not get the usual original TensorFlow style code ever. Okay.